Day 145, Part 2 of Kirchoff's laws, examples 2 and 3. Here we have a single loop with two batteries. Essentially what's going to happen here is the larger battery, the 24-volt battery, will be charging, in a sense, the 6-volt battery. The 24-volt battery is pushing current clockwise here, and the 6-volt battery, with the positive side pointing towards the left, let me label those, is trying to push current counterclockwise, but the stronger battery will win. So there will be a flow of current in the counterclockwise direction, according to this blue arrow here representing current flow. It starts everywhere at all times. It doesn't start from point A or from the batteries, but the current's flowing. The electrons are moving, but this is the conventional current flow direction from positive to negative. And we're going to apply Kirchoff's second law because there are no junctions here, so we cannot even apply Kirchoff's first law. But we don't know the current here. I'm going to call it I. That blue arrow represents the current flow. I'm just going to call it I. Every element here in this circuit has the same current because it's a single loop series circuit. But I will apply Kirchoff's first law to loop A, B, C, D, A. We're going to go around clockwise from point A all the way back to point A. That's a single loop. There are 5 elements there, and I'll just make a generic statement right now. I'm not going to plug in yet, but basically I have V1 plus V2 plus V3 plus V4 plus V5 equals 0. There are 5 elements there. If I start at point A, the first element I come to is the 2 ohm resistor. Now, going with the current flow, the convention is that will be a negative voltage. I'll symbolize it like this. Negative VR2, resistor number 2. Now the batteries are usually plus the 6 volts for the battery as I go from B towards C, but because I'm going into the quote-unquote positive side of the battery, I'm going opposite what that battery typically would be. I'm basically charging that battery. It's going to be a negative 6 or minus 6 volts. And then we have the 0.2 ohm resistor, so it'll be minus VR 0.2 and then minus VR 0.6. But here's the plus now, plus the 24 volts conventional for that battery equals 0. Alright, so it looks like we have 3 unknowns, 3 unknown voltages. But there are some shortcuts we can take here, although the general technique in this case is just using V equals IR to substitute in for V. In other words, for each of those resistors, I'll go to the top here, V equals IR. So for the 2 ohm resistor, it will be VR2, for the 2 ohm resistor, will be the current in that resistor, that's I, times R, but I'll do R times I. I can rearrange those by the commutative property of multiplication. So R is 2, and I'm just going to call that I. So it looks like that doesn't get us anywhere, but it does, as you'll see. The voltage for that resistor, the 2 ohm resistor, is its resistance 2 times the current I, unknown yet. Once again, I can put the R in front. So I'm going to plug that in right now, going back down to the bottom here. In other words, I have negative 2I minus 6. And if I do the same thing for each of the other resistors, I multiply its resistance times its current. It gives me the voltage. So for the 0.2 ohm resistor, it's going to be minus 0.2I, same current, same I. I don't need to call it I sub 2 or I sub 3. It's the same current everywhere in the circuit. Minus, once again, the voltage for the 6 ohm resistor, or the 0.6 ohm resistor, is its resistance 0.6 times I, plus 24 equals 0. And now you'll see you have a 5-term equation here on the left-hand side, or 5 terms, with 3 similar terms that can be combined. The negative 2, the negative 0.2, negative 0.6 gives us negative 2.8I plus 18 equals 0. Combining the 24 minus the 6. Move the 18 over, divide by negative 2.8. You end up with the current in this circuit equal to 6.4 amps. That's an important number. That's not the answer per se, but it's the current flowing. It's an important number because from that I can figure out the power in most of the all the devices. For example here, essentially what's happening is the 24-volt battery is supplying power to this circuit, and I'll go to the right here. Let's use black. So the power of the 24-volt battery, there's two equations for power. There's the definition, P equals VI. That's the definition. Then you can come up with a bunch of other ones, but another one that's useful is P equals I squared R. Now the first one is generally more useful for batteries as they supply or use or become charged, but the battery that's supplying energy here is the 24-volt battery. Its power is just going to be its voltage, 24 volts, times the current supplied, which is 6.4 amps. So the power supplied by that battery is 154 watts. 154 watts. Every other device here is either transferring the energy to heat, the resistors, or being charged, the 6-volt battery, as you'll see as we go along here. For example, the power of the 6-volt battery is its voltage, 6 volts, times 6.4. And in many respects, we can call this a negative. I'm not going to do that right now. I'll show you how this all comes into play in a second. But 6 times 6.4 comes out to be 38 watts. It's absorbing 38 joules of energy per second. The 24-volt battery is putting out 124 joules per second. That's what a watt is. And the resistors are turning it basically into heat. If they're light bulbs, it's turning it into heat and light. But I'll do them one by one. The power of the 2 ohm resistor, P sub 2 for the 2 ohm resistor. Now I'll use I squared R because that's easier for the resistors. It's 6.4 squared times the 2 ohm resistance becomes 82 watts for the 2 ohm resistor. And then we have the 0.2 ohm resistor is going to be 6.4 squared, I squared, times the 0.2. Well, that's just 10 times less. That's just 8.2, or just 8 watts. And then the power used up, or turned into heat and light, or just heat, for the 0.6 ohm resistor is 6.4 squared times 0.6. It'll be just 3 times bigger. If you actually do the math here and round off, it comes out to be 25 watts versus 24 watts. That's not that important. You could have just put 24 watts there. But what I want to show you is this. These 4 numbers, the power supplied to the 6-volt battery to charge it, plus the other 3 numbers here, if you do the math, it comes out to be 153 watts. Now in a perfect world, that would have been 154 watts. The power supplied by the battery is the power used by the devices. The only reason why they're different is because of rounding off. Anyway, there you have it. We have a battery. It's supplying energy at a rate of 154 joules per second, and then the devices absorbing or giving off into other forms of energy 153 joules per second. It checks out. Kirchoff's laws, example 3. Let's review a few things. Once again, the circles represent measuring devices. It's as if they're not there. Ammeters, A sub 1 and A sub 2 here, are placed in series, kind of like as part of the wire, so the current flows through them to make the measurement of the flow of the current. Voltmeters are placed in parallel across the particular device it's measuring. In this case, V sub 1 is measuring the voltage of the battery, the unknown battery voltage for this particular circuit. The letters just all represent locations, only 2 of which are junctions. Points A and D are the only junctions here in this particular circuit where 2 or more wires come together. The other ones are just reference points for when we do our loop analysis for Kirchoff's second law. The blue arrow that I have on the screen here, and also I just remembered, I forgot to label the 2 ohm resistor on your particular handout, so please add that 2 ohm resistor over there by the point B, where the blue arrow is. And it tells you in the problem that A sub 1 is measuring 4 amps. In other words, that blue arrow that I have is a 4 amp current in that branch going from A to B to C to D. So the 2 ohm resistor has a 4 amp current. So, in fact, if I'm looking at that, it's so tempting for me, and if you've done enough of these, you'll see some of these things right away. The 4 amp current is flowing through that 2 ohm resistor, so without even thinking about it, I can calculate, well, thinking a little bit about it, I can calculate the voltage, because V equals IR, Ohm's law, for that 2 ohm resistor down there by point B. I know the R is 2 and the A is 4, so it's 8 volts. I know this is an 8 volt potential difference for that particular resistor. That'll be important as I move along here. Also, I don't know how strong that battery at the top is. The battery at the top is pushing counterclockwise, kind of like in the previous problem, and that battery at the bottom, 2-volt battery, which doesn't sound very strong or has a whole lot of potential, but the battery at the top could be really, really weak. And essentially, when you have two batteries, the general rule is the bigger battery will win. It will push the current its way and will beat the other battery. And in fact, I'm pretty sure that the battery at the top is greater than 2 volts, not just because 2 is a small number, but because this blue arrow at the bottom, the 4 amps, is going to the right. Something has to be pushing that current to the right. More than likely, it's because that upper battery at the very top is really strong, pushing current to G, to H, to A, and splitting between the bottom branch here, that 2 ohm resistor, A sub 1, and the 2-volt battery. So it's likely that this is kind of like the previous problem where there's some charging going on. The current is flowing backward through the 2.0 volt battery at the bottom. Okay, now I will try to apply. Always look for Kirchoff's first law to try to apply that. But in this case, all we know is the 4 amps in that very bottom branch. I don't know the other currents, but you will need to label them. For example, I do know that there will be current flowing from point D to E to F to G to H to A. Okay, that blue arrow that I just drew there has current flowing counterclockwise. I'm predicting that because I'm predicting that the big battery is at the top. If you predict wrong, there's ways to deal with that I'll show you later. But bottom line, more than likely the current's going that way. You should try to put the arrows in the correct direction, most likely direction of the current flow. So that blue arrow I just drew is the predicted flow of current from D to E to F to G to H, and then it splits at point A. 4 amps comes down to B to C to D. That's already given. And there's some current that flows from A to D as well. And that current that I just drew there, I don't know what it is yet, that plus the 4 amps would give me the total current in that upper circle that I drew from D to E to F to G to H. Well, here's the thing now, and I don't know those numbers. All I know is the 4 amps. So I can't really do much with Kirchoff's first law right now. But if I look at this little A, B, C, D, A loop at the bottom here with that 2-volt battery, I know that there are 3 elements there, the 3 ohm resistor, the 2 ohm resistor, and the 2-volt battery. And Kirchoff's second law says in any loop, the voltages must be equal to 0. So in that loop, if I look at the loop A, B, C, D, A, in that order, loop A, B, C, D, A. In other words, if I go around that loop, if I take a walk from A to B to C to D to A, and a lot of times I'll just draw that on there, but it's going to get really messy if I do that now, but I will lightly try to do that. If I go from A to B to C to D to A in that black path that I just drew, it's counterclockwise, there are 3 elements, essentially V1 plus V2 plus V3 has to equal 0. Well, V1, if I'm going from A to B to C, V1 is the 8 volts, technically negative 8 volts for that resistor because I'm going with the flow of the current that I know was given to me as to the right for that 4 amps. That's what started the problem. Then as I go from C to D towards A, I'm going with that battery. If I go counterclockwise around that loop in that same walking path from D to A, that's actually going with that battery. So I'm going to go conventional plus 2 volts for that battery. And then typically, well, then I have plus V3 equals 0. Now, you could have put minus V3 there, but really it doesn't really matter. To be consistent with the way I've been doing it, if I'm going from D to A, and I've got my arrow, my blue arrow pointing to the right, this is unconventional for that resistor, so I would have a positive voltage for that resistor as opposed to the negative voltage. If my black path is against the arrow, the blue path that I drew, the blue arrow, I get a plus V3, but you can also see here pretty easily that V3 is going to be 6 volts. I've kind of overkilled this part of it, but it's 6 volts. Another way to think about this is that the 2 ohm resistor, the 8 volt resistor, really is in parallel with the 3 ohm and the 2 volt battery. And the rule for parallel is any two things, in this case we have 2 things in that branch from A to D, the voltages there must be equal to the 8 volts, because in parallel things have to have the same voltage. So the 3 ohm resistor, you could almost look at this and say, oh, it's got to be 6 volts because the 6 plus the 2 equals the 8, and they're in parallel with the 8, even though you can't combine them like you combine resistors. So in other words, V3, the 3 ohm resistor, has a 6 volt potential difference. All right, now we're making good progress here. We're looking for A sub 2 and V sub 1, and we're going to look at this upper loop now. And it doesn't really matter where you start. You start at H, A, D, E, F, or G. But if you take that loop, let's just call it, and I'll go up here, loop, start anywhere you want. Let's go from G. G to H to A to D to E to F and back to G. So I'm going around that loop. I'm taking a walk. And I've already drawn in what the current would look like in blue. And it's going to coincide with the way I'm taking my walk here. But if I go from G to H to A to D to E to F to G, I encounter 4 elements. So generically I'll just write V1 plus V2 plus V3 plus V4 has to equal 0 around that loop. So when I go from G to H to A to D, the first thing I hit is that 3 ohm resistor, which I already know is 6 volts, but now I'm going with the current flow. I'm going with my blue arrow as I'm taking this walk from H to A to D. So that will be the typical negative 6 volts for that particular resistor. And I'm going backwards through that battery now as opposed to the first time in loop A, B, C, D, A. Now I'm going into the positive part of the battery, the long line, towards the negative. So that would be unconventional. That's minus 2 this time as I go from left to right. The other time I went from right to left. We'll have to practice that. Okay, so that's minus 2. And then I go from D to E. I'm passing through the 5 ohm resistor, and I'm going with the flow of the blue arrow. So that's conventional as well. That's going to be minus the voltage of that resistor. So that's minus VR5. And then plus V4, because I'm going to be going with that battery. I'm going into negative conventional equals 0. Well, I got a problem here. I have 2 unknowns. So I'm scratching my head a little bit, but now I just realized we could have actually figured out the current through the 3 ohm resistor because we know the voltage of the 3 ohm resistor. So I'm going to back the truck up here a little bit and calculate that. V 3 ohm resistor equals I for the 3 ohm resistor times R of the 3 ohm resistor. And we calculated V3 to be 6 volts. The current was unknown, but the resistance is 3. So the current through that resistor, I3, is 2 amps. That's an important number because the 2 amps goes from A to D. And now if we look at junction D, we can go back to Kirchoff's first law. We have 4 amps going from B to C up into D, and then from A to D we have 2 amps. We have 6 amps going into junction D. Therefore, we must have 6 amps coming out of junction D, so that there must be 6 amps. This blue arrow up here must be a 6 amp current because it has to be the 4 plus the 2 gives you 6 amps. Or in other words, there's 6 amps going through the 5 ohm resistor. Therefore, for the 5 ohm resistor, which is part of that 6 amp branch current, V5 equals I5 R5. So V5 is 6 amps times 5 ohms. V5 equals 30 volts. I should have done that earlier, but now I can go back up to my loop upper here right, where I have the -6 minus the 2, which is -8. So -8, and then minus V5, which I now know is 30, plus V4 equals 0. Therefore, V4, which is actually the voltage of the battery, which is really V1, but I didn't change that yet. But that just says that V4 has to be 38 volts. That's the voltage of that unknown battery, which is V sub 1 technically. Should have put that in there. I'm getting a little sloppy with the subscripts here, but that V sub 4 stood for the voltage of that battery, which is really where the meter V1 is. So we just successfully solved the problem. We have V1, 38 volts, and we have the current A sub 2, the meter, A2, it will be 6 amps. So there we have it. It all falls into place right there at the end. We've solved for the current in that upper branch and the voltage of that unknown battery. Kirchoff's laws, once again, they're very useful laws in solving some of these more complex circuits.